In this video, we will be going over section 2.2. In this section, we will be giving the formal definition of derivative. Okay, basically, we are going to define formally what we mean by the derivative of a function at a given point. Okay. First, I want to start with this definition: derivative of a function at a point. Okay, what do you mean by the derivative of a function at a given point x is equal to c? The derivative at x is equal to c of a function f is the number defined by this limit. Okay. By the way, the derivative at x is equal to c is denoted by f prime of c. Okay, we know that from the previous section, and here is how you define it. Okay, the derivative at x is equal to c is defined by this limit as h approaches to 0, f of c plus h minus f of c divided by h. Okay, this limit will give you the derivative of the function f at x is equal to c, if of course, if this derivative exists. Okay, if this limit exists. Okay, if this limit does not exist, the derivative at that point does not exist. Okay, all right, rather than taking this merely as a definition, let's try to understand what this definition really tells you. Okay, to understand that, let's forget about this limit part. Let's try to understand this piece. What does this mean? From the last section, we know that this is the slope of the secant line joining these 2 points, right? Joining the points c comma f of c and c plus h comma f of c plus h. Okay, let's say here is the graph of your f of x. Let's say this point c is here, then this point has to be, the y value has to be f of c. Now I'm going to take a neighboring point c plus h. Of course, this h is a positive quantity. That's why the c plus h is in the right hand side. If h is negative quantity, it has to be c plus h has to be in the to the left of c. Okay. So if I take this to be c plus h, my y value would be f of c plus h. Now, what is this quantity? Clearly, that quantity is nothing but the slope of this secant line. Secant line means you join these 2 points to get the secant line. Okay, this is your secant line. The slope of this line is given by this quantity without the limit. Okay, then what happens to this quantity as h approaches to 0? First of all, notice that f prime of c is the derivative of the function at x is equal to c. What does that mean? That means derivative of the function f of x at x is equal to c means the slope of the tangent to my function at x is equal to c. So I'm drawing a tangent to my function at x is equal to c. Okay, in blue is my tangent to my function at x is equal to c. Okay, so f prime of c means the slope of this tangent line. What I'm going to do is I'm going to approximate the slope of this tangent line by the slope of this secant line. Would that be a good approximation? Well, it will be a good approximation if you choose this h to be small. What happens is that if you choose your h to be small, your c plus h will be closer to c. Okay? For example, if you choose your h to be more smaller than this h, your c plus h would be somewhere here. In that case, your secant line would be this line. As you can see, the slope of this newly drawn secant line is closer to the slope of the blue line than the previous secant line. Okay, so that's the idea. When your h is getting closer and closer to 0, this secant line becomes, I'll draw the set of secant lines. The secant line would become like this. Those secant lines are getting closer and closer to the blue line. What does that mean? That means the slope of those secant lines are getting closer and closer to the slope of this blue line, which is the slope that we are looking for. Okay. Then when you take limit as h approaches to 0, this quantity, this limit will give you the slope of the function at x is equal to c. Or in other words, it will give you the slope of this tangent line if you take the limit as h approaches to 0. Okay, that's the idea. And of course, we have an equivalent definition. These two definitions are equivalent. Okay, you can either find this limit to find the derivative of f at x is equal to c, or you can use this definition. Limit as z approaches to z, f of z minus f of c divided by z minus c. Okay, these two definitions are equivalent. You will be proving this equivalence in your homework assignment. Okay, and by the way, this is a remark: the derivative of a function f at a point x is equal to c measures the instantaneous rate of change of the function at x is equal to c. Okay, so this instantaneous rate of change is the same as the derivative. Okay, instantaneous rate of change of a function is the same as the derivative of the function. They are kind of synonyms. Okay, derivative, instantaneous rate of change. All right, so this is the definition of the derivative at a point x is equal to c. We need to be able to use both of these definitions to find the derivative. Doesn't matter what definition you use, both definitions should give the same answer. Okay. Okay, now we are going to define the derivative of a function. Remember, here we define the derivative of a function f at x is equal to c. This c is a particular point. Okay, now we are going to define the derivative of a function at a general point x. X is any arbitrary point. Okay, here is how you define it. The derivative of a function f is the function f prime. Of course, there's a typo here. This should be f prime. Okay. The derivative of a function f is the function f prime defined by f prime of x is equal to limit as h goes to 0, f of x plus h minus f of x divided by h. All I do is I go to this particular definition. This is the definition of the derivative at x is equal to c. Now I replace my c by x. That's all I do. That way I get the definition for the derivative of my function f of x at a general point x. So that will give you this definition. Okay, this is what we mean by the derivative of a function f. Okay, equivalently, we can use the other definition to define the derivative of a function. F prime of x is given by limit as z approaches to x. Remember, in the previous definition, z approaches to c, but here we have a general point x. Limit as z approaches to x, f of z minus f of x divided by z minus x. All I do is I replace my c by x. If you look at the previous definition here, I replace my c by x. X is a general point. And then the domain of f prime is the set of x for which the defining limit of f exists. Okay, if this limit exists, that particular x is in the domain of your derivative function. Okay, this is the derivative as a function, f prime of x. All right, let's do some examples to understand these two definitions. Here is the example I want to look at first. Consider the function f of x is equal to x squared. Use h goes to 0 definition of the derivative to find f prime of x. That means we are asked to use this definition first, and then in the next part, we are asked to use this definition to find the derivative. Remember, no matter what definition you use, you should come up with the same answer. Okay. All right, let's work on the first part. Let's use the h goes to 0 definition. Okay. By that definition, f prime of x is equal to limit as h goes to 0, f of x plus h minus f of x divided by h. That is the h goes to 0 definition. Okay. Now let's try to compute this one. I want f of x plus h. F of x is given. How would I find f of x plus h then? You plug in x plus h in this function, right? So then you get x plus h squared minus f of x. What is my f of x? That is x squared divided by h. By the way, I'm forgetting something very important. What is that? The limit. limit as h goes to 0. Okay. Now let's clean this up a little bit. Okay. Let's clean up the top. Then you get this is equal to limit as h goes to 0. X plus h squared is x squared plus 2xh plus h squared minus x squared divided by h. Now, as you can see, x squared, they are cancelled. We cancel them. What do you get in the top? The top, you have limit as h goes to 0, 2xh plus h squared. Okay, I'm going to pull out an h, then you get h times 2x plus h. Okay, of course, you get 2x plus 2xh plus h squared. I'm pulling out an h, then you get h times 2x plus h divided by h. Now, as you can see, you have a cancellation. H and h will be cancelled. Okay, if I cancel those, then here is the limit I get. Limit as h goes to 0, 2x plus h. Now, all you need to do is to take the limit of this expression. So this is a summation. You can kind of distribute this limit inside the parentheses. You take the limit of the first term, and then you take the limit of the second term. In the first term, there is no h involved. That means the limit of this term is that itself, 2x. Then you take the limit of this one, this expression, as h goes to 0. That limit is 0, because when h goes to 0, this value is 0. Okay, plus 0, which is of course 2x. That means your f prime of x is nothing but 2x. Okay, now let's use the other definition. Okay, z goes to x definition. Okay, all right, let me add a page here. Here is the other definition. F prime of x is equal to limit z goes to x, f of z minus f of x divided by z minus x. Okay, I'm just copying this definition, the second definition. I'm copying this second definition. Okay. All right, so let's proceed. So to find this limit, what I'm going to do is this is equal to limit z goes to x. Excuse me. Z goes to x, f of z. F of z is z squared minus f of x is x squared divided by z minus x. I can simplify this a little bit. Limit z goes to x, z minus x, z plus x. I'm of course factorizing my top, divided by z minus x. Now, by cancellation for limits, we can cancel these two common factors, z minus x, they will be gone. You are left with c plus x. Notice that you are left with c plus x. Let me write that here. Limit as z goes to x, c plus x. What is this limit? You can again take the limit of the first term and the limit of the second term individually. If you take the limit as c approaches to x of the first term, this will become x, right? Because your z approaches to x, then this becomes x. This x will stay as it is, because as c approaches to x, nothing will happen to x. So this will look like x plus x, which is 2x. Notice that this case, f prime of x is equal to 2x. In the previous case also, we got the same as. Okay. Remember, no matter what definition you use, you should come up with the same as. All right, what is the next part? Graph the function f of x is equal to x squared and the derivative f prime of x you found in parts A and B. Of course, from parts A and B, both we found the same derivative. Okay, we found the same derivative. We are asked to graph both f of x and f prime of x and argue that one graph is the slope function of the other graph. Let's quickly graph those two functions. It is the graph of the f of x. Maybe somewhere here. This is your f of x. This is x-axis. Of course, you know the graph of f of x. It's a parabola like this. And then the derivative, f prime of x, which is equal to 2x. This is f of x is equal to x squared, okay? That is the graph of parabola like this. And what is the graph of this one? F prime of x is equal to 2x. It's a straight line, right? This is mx plus c form. Y is equal to mx plus c form. Of course, your value of c is 0. So you get a straight line like this. This is the graph of f prime of x. So what do you think? Would you believe this? This is the slope function. F prime of x is the slope function, right? Slope of f of x. So would you believe that this is the slope function? Well, let's make few observations here. If you look at this graph, to the left of 0, your slope of this function is negative. It is clear. If you take any point to the left of 0, if you draw a tangent to your function f of x at that point, slope of that tangent is negative. That means slope of this function, this particular function, to the left of 0 is always negative. That's why this slope function stays below the x-axis to the left of 0. As you can see, your slope is a negative value to the left of 0, and to the right of 0, your slope is a positive value. Okay? It should be, because see, if you look at this graph, to the right of 0, you have a positive slope. No matter what point x value you pick, for that x value, the slope of the tangent to your graph, f of x, graph of f of x is positive. So slope is positive for all x values to the right of x. That's why this graph, the slope function, stays above the x-axis for x bigger than 0. Okay, so the slope ideas that we discussed in section 2.1 very well go with what we have here. Okay, let's move on. Next, I want to introduce some of the notations. Okay, here are the notations that I want to introduce to you. Sometimes to denote f prime of x, remember f prime of x is the slope function or the derivative of f of x. Okay, so the derivative of f of x is denoted by f prime of x. We also use this notation to denote the same thing. Okay, derivative of f of x is denoted by either f prime of x or df over dx. df over dx. Okay, this notation is also used to denote the same thing, the derivative of f of x. And also, if the function is given in this form, y is equal to f of x, then we denote the derivative of f of x this way, dy over dx. dy over dx means the derivative of f of x. It means the same thing. For example, in the previous case, notice that if your function was given as y is equal to x squared, then dy over dx means the derivative of this function. Of course, in the previous case, it wasn't given as y is equal to x squared. It was given as f of x is equal to x squared. What I'm saying is, if it was given as y is equal to x squared, we denote the derivative of this function by dy over dx. dy over dx means the derivative of this function, which is of course 2x. You found it in the previous example. Okay, those are some notations that you need to get familiar with. Okay, next, what do you mean by d squared y over dx squared? We know what is, let's look at the previous example, okay? I'm looking at the previous example. I know that if my y is equal to x squared, I know that dy over dx, the derivative of that function is 2x. I just found it. As you can see, f prime of x is equal to 2x. Okay, if my function was given as y is equal to x squared, then the derivative of that function is dy over dx, which is 2x. I found it. Okay, so dy over dx is 2x, given that your function is y is equal to x squared. Then what do we mean by d squared y over dx squared? Well, that is very simple. What you do is, this is the first derivative of the original function given to you. D squared y over dx squared is the second derivative. What you do is, you take the derivative of this function one more time. Okay, you took the derivative of this function to get this one. Now you take the derivative of this one more time to get the second derivative. This is called the second derivative of the given function y is equal to x squared. Okay, so that's just into the notation. So let's find the second derivative actually. How do I find the second derivative? D squared y over dx squared is equal to, I have to take the derivative of this function one more time. Okay, so for that, I'm going to use the same definition. This is the definition of the derivative. Okay, I'm using this definition to find the derivative of this function. Now you pretend like your f of x is this function. This is your f of x. Okay, then by this definition, you get limit as h goes to 0, pardon me, h goes to 0, f of x plus h, that is 2 times x plus h minus f of x, 2x divided by h. If you clean up the top, you get limit as h approaches to 0, 2h divided by h. This is 2x, that will be cancelled with this minus 2x, you will get 2h in the top. Now, of course, by cancellation law, you can cancel h in the top and h in the bottom. You get 2, because the limit as h approaches to 0, a constant, 2 is 2 itself. Okay, this is the second derivative. D squared y over dx squared is that. Dx squared is equal to 2. All right, let's move on. Okay, next thing I want to talk about is this definition 2.3, differentiability at a point. When do you say that a function is differentiable at a point x is equal to c? This is when you precisely say that a function f of x is differentiable at x is equal to c. Here is the definition. A function f is differentiable at x is equal to c if this limit exists. Okay, notice that this is the definition of the derivative of f of x at x is equal to c. Okay, so we say that the function f is differentiable at x is equal to c if the derivative exists at x is equal to c. Okay, if the derivative of f of x exists at x is equal to c, then we say that the function is differentiable at x is equal to c. Okay, so that's a definition. Okay, next we are going to talk about one-sided differentiability. Remember when we were talking about limits, continuity, we had a similar scenario. Okay, when we were talking about limits, we had left limit and the right limit, right? When we were talking about continuity, we had left continuity and right continuity. Likewise, here we have something called left differentiability and right differentiability. Okay, here is the definition. The first of all, we define the left derivative and the right derivative of a function f. The left derivative and right derivative of a function f at x is equal to c are respectively equal to the following if they exist. Okay, here is the definition of left derivative at x is equal to c. Okay, f prime, here is how you denote it, by the way. F prime, you put a minus sign to indicate that that is the left derivative at x is equal to c, that is defined by this limit. Okay, limit as h approaches to 0 from the left hand side. You have a minus sign here. Notice that you have minus sign here. That means h approaches to 0 from the left hand side. F of x plus h minus f of c divided by h. And here is the definition of the right derivative at x is equal to c. You put a plus sign to indicate that it is the right derivative. F prime plus of c is equal to limit, this time as h approaches to 0 from the right hand side. F of c plus h minus f of c divided by h. Okay, notice that these two definitions are kind of a modification of the original definition of the derivative. recall that the derivative of a function f at x is equal to c is given by limit as h goes to 0, f of c plus h minus f of c divided by h. Now to get the left derivative, you put a minus sign here. To get the right derivative, you put a plus sign here. Okay, so that's how you modify the original definition to get the definition for the left derivative and the right derivative. Okay. By the way, here we can use a similar definition. We can use the z goes to c definition as well, but I'm not going to go to that definition. In that case, what you do is to define the left derivative, you put z minus here. To define the right derivative, you put c plus here. That's the only difference. Okay. All right. And then here is an important remark. A function is not a remark, actually, this is a definition. Okay. A function is left differentiable at x is equal to c if f prime minus z exists. Okay, that means the left derivative exists. If the left derivative at x is equal to c exists, then we say that that function is left differentiable. And if the right derivative at x is equal to c exists, we say that the function is right differentiable. And here is the remark. A function is differentiable at x is equal to c if and only if the left derivative and the right derivative exist and they are equal. That's very important. Okay, you can use this remark to check the differentiability of a function at a given point. Okay, this is a very powerful remark. Okay, now let's look at some example. Here is the example that I want to work on first. Is the function f of x is equal to absolute value of x differentiable at x is equal to 0? Would this be differentiable at x is equal to 0? Well, we can check. Okay, we can use this remark, the previous remark that we made, to check that. Okay, a function is differentiable at x is equal to a z if and only if the left derivative and the right derivative at that point exist and they are equal. So what you do is you compute the left derivative at x is equal to 0 and the right derivative at x is equal to 0 and check whether they are equal. Okay, they should exist and they should be equal if the derivative at x is equal to 0 exists. If your function is differentiable at x is equal to 0. So let's find the left derivative and right derivative at x is equal to 0 for this given function. Okay. Okay, all right. Let's find the left derivative, the right derivative at x is equal to 0 first. F prime of plus 0 is equal to limit by definition. By the way, the right derivative definition is given here. Limit h approaches to 0 from the right hand side. F of 0 plus h. Remember, the point that I'm interested in is 0. Your c value is 0 in this case. That's the point that I'm interested in. So this is equal to the f of 0 minus h minus f of h divided by h. Okay. Now let's simplify this a little. Pardon me, this has to be 0. Okay, this is my value of c is 0. This has to be f of c, that is f of 0. Okay, now if I simplify this a little bit, if I simplify my numerator, you get f of h minus f of 0. What is f of 0? To find f of 0, you plug in 0 here. Absolute value of 0 is 0. Divided by h. This is, of course, limit as h approaches to 0 from the right hand side. F of h. F of h is absolute value of h divided by h. Now, how do you handle this one? to find this limit, first of all, you need to get rid of this absolute value. Notice that your h is approaching to 0 from the right-hand side. That means h is a positive number. If it is a positive number, this quantity can be written as, this is equal to limit as h approaches to 0 from the positive side, h divided by h. Your absolute value of h is same as h because h is a positive number, right? Now, by cancellation law, you can cancel these two quantities. H and h will be cancelled. That number is 1. H divided by h is 1. The limit as h approaches to 0 plus 1 is 1 itself. So the answer is 1. Okay, so the left derivative is, the right derivative is 1. The right derivative is 1. Now let's check the left derivative. Okay, now I want to find limit as h approaches to 0 from the left-hand side. Pardon me. Let me write the notation first. F prime of prime minus of 0 is equal to limit h approaches to 0 from the left-hand side, f of 0 plus h minus f of 0 divided by h. Okay, let's simplify this. This is equal to limit as h approaches to 0 from the left-hand side. What do I get here? Left-hand side, f of 0 plus h, which is f of h. This is f of h. F of h is absolute value of h minus f of 0. Again, my f of 0 is 0 because you can plug in 0 here to find my f of 0, which is 0, divided by h. This will be equal to limit as h goes to 0 from the negative side or the left-hand side, absolute value of h divided by h. Now, again, to find this limit, I need to get rid of this absolute value. How do I get rid of my absolute value? Notice that your h is approaching to 0 from the left-hand side. That means you can think of h as a negative number since it is approaching to 0 from the left-hand side. So to get rid of this absolute value, I have to put a minus sign. Okay, so this will be equal to limit as h approaches to 0 from the left-hand side minus h divided by h. That's how you get rid of, by the way, don't get confused with this minus sign, okay? This minus sign is top of this 0 to indicate that h is approaching to 0 from the left-hand side. I'm going to replace this absolute value of h by minus h. Because my h is negative, I have to have a minus sign when I get rid of the absolute value, okay? So now, again, I can cancel this h and h. Then you get minus 1, okay? So this limit would be minus 1. Notice that your right derivative is plus 1 and your left derivative is minus 1. They are not equal, okay? So the derivative at x is equal to 0 does not exist. Me write it. F prime minus 0 is not equal to f prime plus 0. The right derivative and the left derivative, they are not equal. So the derivative, or you can say the function, is not differentiable at x is equal to 0. Okay, that's the conclusion, because the left derivative and the right derivative are not equal. All right, let's move on. Let's work on another example. Consider the piecewise defined function f of x is equal to 3x plus 2 if x is less than 1, and f of x is equal to 6 minus x if x is greater than or equal to 1. The first part asks you to calculate f prime plus 1 and f prime minus 1. That means you are asked to calculate the right derivative and the left derivative at x is equal to 1. Okay, and then you are asked, what can you say about f prime of 1? Or in other words, you are asked whether f prime of 1 exists or not. Okay, to answer this question, let's find f prime plus 1 and f prime minus 1, the right derivative and the left derivative. Okay, let's copy everything to a new page. Let's find the right derivative first. Okay, this is the definition of right derivative at x is equal to 1. F prime plus of 1 is equal to limit as h approaches to 0 from the right hand side, f of 1 plus h minus f of 1 divided by h. Okay, let's find that. This is equal to limit as h approaches to 0 from the right hand side, f of 1 plus h. How do you find f of 1 plus h? When h approaches to 0 from the right hand side, this quantity is a quantity which is bigger than or equal to 1, right? It's bigger than 1. Okay, if this quantity is bigger than 1, this is the right piece of function. When x is bigger than or equal to 1, when your input is bigger than or equal to 1, this is your function, 6 minus x. So that means this is the function that I need to use to compute f of 1 plus h, because this quantity is bigger than 1, since h approaches to 0 from the right hand side. Okay, so I'm going to use this piece of function to calculate f of 1 plus h. So if I do that, you get 6 minus 1 plus h. I'm just plugging 1 plus h in this function. Okay, that's all I'm doing. So that is f of 1 plus h. Don't forget, I have minus f of 1. Minus f of 1. To find f of 1, I have to plug in 1 in my function. So I have to plug in 1 in this piece of function, because this is valid when x is greater than or equal to 1. Okay, so I'm going to plug in 1 here to find f of 1. 6 minus 1 divided by h. Now it's all about simplifying your numerator. Limit as h approaches to 0 from the positive side. If you simplify your top, you get 6 minus 1 minus h minus 6 plus 1. Of course, I distributed this negative sign here. Now, as you can see, we have a bunch of cancellations. These two will be cancelled. These two will be cancelled, minus 1 plus 1. Don't forget to h in the bottom, okay? So now this is equal to limit as h approaches to 0 from the positive side minus h divided by h. Now again, by cancellation law, I can cancel this h and h. You get minus 1. So the limit as h approaches to 0 minus 1 is just minus 1. Okay, maybe let me write one more step here to make it clear to you. This is equal to limit as h approaches to 0 from the positive side minus 1, which is equal to minus 1, because minus 1 is a constant. Nothing happens to minus 1 as h approaches to 0. Okay, so that is minus 1. Now let's compute the left derivative. Okay, now we are going to compute the left derivative. Here is the definition of left derivative. Maybe I will copy this over here. Okay, so let's compute this one. This is equal to limit as h goes to 0 from the negative side, f of 1 plus h. Remember, now h is approaching to 0 from the left-hand side. That means this is a quantity which is less than 1. So this is the right piece of function that you need to use to find f of 1 plus h this time. Okay, because I know that 1 plus h is a number which is less than 1. When x is less than 1, here is the right piece of function. So let's find f of 1 plus h using that correct piece. 3 of 1 plus h, 3 times 1 plus h plus 2, that is your f of 1 plus h, minus f of 1. What is my f of 1? I need my f of 1 here. Of course, to find f of 1, I have to plug in 1 in this piece of function because this function is valid when x is bigger than or equal to 1. Okay, so I'm plugging 1 here. That will give you 6 minus 1. Okay, divided by h. Now, if you simplify this, limit as h approaches to 0 from the left-hand side. If you simplify your top, you get 3 plus 3h plus 2 minus 5 divided by h. Simplifying this, you will see that this is going to be equal to h goes to 0 from the left-hand side, 3h divided by h. The answer is clearly 3 because I can cancel this h and h. The limit as h approaches to 0, 3 is 3 itself. Okay, so we get the left derivative to be 3. As you can see, f prime plus 0 is not equal to f prime minus 0. That means the derivative at 0 is not defined, or the derivative at 0, at 1. Or this should be 1 actually. Sorry about that. Let's make that change. Your left derivative, right derivative at 1 is different from the left derivative at x is equal to 1. So the derivative at x is equal to 1 is not defined in this case. Or in other words, f is not differentiable at x is equal to 1. That's the conclusion. Okay. All right, let's move on. And then we have one more part. Write down a formula for f prime of x as a piecewise defined function. How do you write down a formula as a piecewise defined function? First of all, notice that we know that my function is not differentiable at x is equal to 1. We have already concluded that. Now let's find the derivative of the function when x is less than 1. This is the function when x is less than 1. And then let's find the derivative of the function when x is greater than 1. Okay, so that's the idea. Let me first find the derivative of my function when x is greater than 1. When x is greater than 1, here is the function that I need to be looking at. Then my f of x is 6 minus x. Let's find the derivative of this function using the definition. Okay, my f prime of x is limit as h goes to 0, f of x plus h minus f of x divided by h. This is equal to limit as h goes to 0, f of x plus h, which is 6 minus x plus h minus f of x. F of x is 6 minus x divided by h. If you simplify this, you will get limit as h goes to 0. Notice that this 6, they will be gone. Here you have a minus x, and here you have a plus x. Those two will be gone. What is remaining is minus h divided by h. The limit of this one will be clearly minus 1 because you can cancel these two and you get minus 1. The limit as h approaches to 0, minus 1 is minus 1 itself. So we found that limit. And then let's find the derivative when x is less than 1. When x is less than 1. Okay. Then my function is when x is less than 1. Notice that my function is 3x plus 2. Let me use that function. 3x plus 2. Again, I'm going to use the definition. F prime of x is equal to limit h approaches to 0, f of x plus h, that is 3 times x plus h plus 2 minus f of x. Minus f of x means 3x plus 2 divided by h. Let's simplify the top. Again, you will have a bunch of cancellations. You have 3x here. You have minus 3x here. Those two will be cancelled. And you have minus 2 here. You have plus 2 here. Those two will be cancelled. What is remaining in the top is 3h. In the bottom, you have h. Now, if you cancel h in the top and h in the bottom, you get 3. The limit as h approaches to 0, 3 is 3 itself. So that means the derivative when x is bigger than 1, your f prime of x is minus 1. When x is less than 1, f prime of x is plus 3. So we can write a piecewise function for f prime of x. Okay, here is the piecewise function. When x is, pardon me, this is minus 1. When x is bigger than 1 and it is undefined, when x is equal to 1, we saw that it was not defined, derivative was not defined at x is equal to 1. It's not differentiable at x is equal to 1. Okay. And of course, it is 3 if your x is less than 1. This is the piecewise function for the derivative f prime of x. Okay. All right, let's move on. Next, we have this interesting theorem which gives you a connection between differentiability and continuity. Let's see what it says. Okay, differentiability implies continuity. Okay, if f is differentiable at x is equal to c, then f is continuous at x is equal to c. Or in other words, the differentiability at a point x is equal to c implies the continuity at x is equal to c. Okay, or in other words, the differentiability is a stronger condition than continuity. Let's quickly prove this. Proof. Okay, here is how the proof goes. First, let's assume that my function f is differentiable at x is equal to c. Then I must show that my function is continuous at x is equal to c, right? To show that my function is continuous at x is equal to c, all I need to show is, I need to show that limit as x approaches to c, f of x is same as f of c. This is the definition of continuity that we learned in chapter 1. Okay, if f is continuous at x is equal to c, limit as x approaches to c, f of x should be equal to f of c. This is what I'm going to show. Okay, for that, let's consider this expression. Okay, this particular limit. Okay, I want to compute limit All right, so I'm going to consider this particular limit as x approaches to c, f of x minus f of c. Okay, so now I'm going to do a small construction here. Limit as x approaches to c, f of x minus f of c. Tell me whether you agree with me. Okay, x minus c times, I'm going to put a x minus c here, you know, kind of, this will be cancelled, then you get back what you had, right? So this is a construction which is valid. Okay, so I multiply both top and bottom by x minus c. Now I can view these as two functions. The first function, this is the first function, this is the second function. Now I can take the limit of these two functions individually by limit rules that we learned in section 1.6. Okay, limit, chapter 1. All right, let's find the limit. Limit as x approaches to c, f of x minus f of c divided by x minus c times the limit as x approaches to c, x minus c. Now, what is this limit? Isn't this the derivative of f at x is equal to c? By the second definition of the derivative, notice that the second definition of the derivative is this c definition, right? This is the second definition. Using this definition, we clearly see that this part is nothing but the derivative of f of x at x is equal to c. So this is f prime of c. And we are given that my function is differentiable. I'm assuming that my function f is differentiable at x is equal to c. What does that mean? That means this exists. F prime of c exists. This times, this is f prime of c, times the limit of this expression. What is the limit of this one? Limit as x approaches to c, x minus c. It is clearly 0. Because when x approaches to c, this becomes c minus c, which is 0. This will give you 0. That means this limit is 0. What does that tell you? That tells you that limit as x approaches to c, f of x minus limit as x approaches to c, f of c is equal to 0. I just distributed this limit to each individual term. Okay, so that should be 0, but this is a constant. F of c is a constant. The limit of a constant is that constant itself. This will give you limit as x approaches to c, f of x is equal to f of c. Because this limit is just f of c. If you move that to the other side, this is what you get. That's what exactly I wanted to prove. So that means my function f is continuous at x is equal to c. Okay, we quickly write it. Continuous at x is equal to c. This is the concluding statement. X has to be continuous at x is equal to c. All right, let's move on. Let's look at this example. So you are given the graph of f of x this way. And here is the question. Where is this function not differentiable? Okay. Before I do this, I want to quickly go back to the absolute value example. This is the absolute value example we did. We answered the question whether my function f of x is equal to absolute value of x is differentiable at x is equal to 0. We say that it is not differentiable at x is equal to 0. If you look at the graph of absolute value of x, you know that, you all know that from your pre-calculus class, the graph looks like this, V-shaped, right? And we saw here that my function is not differentiable at x is equal to 0. Here, what happens is that, as you can see from the graph, you have a sharp corner here, right? You look at the graph here, you have a sharp vertex, sharp corner. If you have sharp corners in your graph, at those points, your function is not differentiable. Okay, so with that in mind, let's answer the question here. Where is this function not differentiable in the given interval? Okay, what are the points would this function not be differentiable? Clearly, at x is equal to 1, it is not differentiable because you have a sharp corner. See, you have a sharp corner, so it's not differentiable. If it is differentiable, it has to be smooth. Okay, and then let me write it. Okay, f is not differentiable at x is equal to 1. What else? What about in this piece? This piece, your function is very smooth, right? There is no sharp corner or discontinuity. So that means it is differentiable. Even this piece. In this interval, from all the way up to here, but not including 1, your function is differentiable because this is a smooth curve. Here, between 1 and 2 also, you have a smooth curve. So it's differentiable. But here, your function is discontinuous. It's not continuous. If it is discontinuous, it is not differentiable. At x is equal to 2 also, your function is not differentiable. Okay? All right. Again, why is it not differentiable at this point? Because, as you saw, it is not continuous at this point, but the previous theorem tells you that if f is differentiable at x is equal to c, then it has to be continuous. But this is not continuous. If it is not continuous at x is equal to 2, it cannot be differentiable because the differentiability implies the continuity. Okay, so my function is not differentiable at x is equal to 2. And what other points? Comma, at this point. Again, you have an infinite discontinuity, so your function is not differentiable at x is equal to, say this point is 3, x is equal to 3. So at these points, your function is not differentiable. Okay, so you need to be able to identify at which point a given function is not differentiable. All right, let's move on. Next, we have this theorem, the equation of the tangent line to a function at a point. The tangent to the graph of a function f at the point x is equal to c is defined to be the line passing through c comma f of 3 with slope f prime of c, provided that the derivative f prime of c exists. This line has the equation y is equal to f of c plus f prime of c times x minus c. Okay, let's try to understand the geometry a little bit here. Okay, let's see whether this given story is true. Say, for example, you have been given your graph of y is equal to f of x. Say your graph of y is equal to f of x is this one. This is the graph of y is equal to f of x. Then you want to find the equation of the tangent line at a given point C. Let's say your point C is here. You want to find the equation of the tangent to your f of x at this point, x is equal to c. This is the tangent line, right? This is the tangent to your f of x at x is equal to c. You need to find the equation of this tangent. But we know that by our previous arguments, the slope of this tangent line is f prime of c. That is the derivative at x is equal to c. By definition, the derivative at x is equal to c is the slope of the tangent to f of x at x is equal to c. Okay, so I know the slope of this line. And I also know that this y value is f of c. F of c. That means this point is nothing but c comma f of c. What I am interested in is to find the equation of this tangent line. Can I find this equation of this, this tangent line given this information? I know the slope, I know a point that it passes through. Well, I can use the point slope form of the line to find the equation. Y minus y1 is equal to m times x minus x1. If I use this form, I get y minus y1. y1 is f of c is equal to m times. My m is f prime of c. M is the slope times x minus c. Okay, this point is c comma f of c. That means your y1 is f of c, your x1 is c. If I simplify this, I get this equation. That is the equation of the tangent to f of x at x is equal to c. F of c plus f prime of c times x minus c. Okay, so that's the idea. Let's move on. And let's work on this particular example. Suppose f of x is given to be this function. Find f prime of x and the equation of the tangent line to f at x is equal to 1. Okay. Well, this is how you find the equation of the tangent from the previous theorem. Y is equal to f of c plus f prime of c times x minus 1. Of course, I can find my f of c quickly. By the way, the value of c in this case is 1. Okay, this is my value of c. Okay, so I want to find this equation. Y is equal to f of 1 plus f prime of 1 times x minus 1. That is the equation of the tangent, right? From the previous formula that we learned, y is equal to f of c, my c is 1, plus f prime of c, that is f prime of 1, times x minus c, c is 1. Okay, so all I want to do is I need to find f of 1. Finding f of 1 is easy. Why? Because you just plug in x is equal to 1 in your function. Okay, I can easily find f of 1 by plugging 1 in my function, that is square root of 1, which is 1. So I have this quantity. All I need is this quantity. Let's quickly find it. Okay, so how do I find f prime of 1? By definition, that is limit as h approaches to 0. H approaches to 0. F of 1 plus h minus f of 1 divided by h. Let's compute this. F of 1 plus h. What is that? That is going to be square root of 1 plus h minus square root of 1, which is 1 itself, of course, divided by h. I'm forgetting my limit here. Let me put the limit. Limit as h approaches to 0. Okay, so if you simplify this a little bit more, limit as h approaches to 0, you have 1 square root of 1 plus h minus 1 divided by h. Now we have a problem. What is the problem? You cannot find this limit straight away. You cannot plug in h is equal to 0. If you plug in h is equal to 0 in the top, you get square root of 1 minus 1, which is 0. In the bottom also, you get 0. So you need to find some sort of a strategy to find the derivative here, find this limit. Okay, what you do is, the strategy that we use is you multiply both top and bottom by the reciprocal of this expression. Reciprocal means you switch the sign in the middle. Okay, so you multiply both top and bottom of that expression by 1 plus square root of 1 plus h plus 1 divided by square root of 1 plus h plus 1. Okay, I multiplied both top and bottom of this expression by the reciprocal of your numerator. That is, you put a plus sign. That's when you get this quantity. Okay, now let's do some simplification here. This is equal to limit as h goes to 0. In the top, notice that we have this times this. Let me write it. 1 plus h minus 1 times 1 plus h square root of 1 plus h plus 1 divided by h times square root of 1 plus h plus 1. Okay. Now notice that this looks like the difference of two squares factors, right? It's a minus b, a plus b. So that should be equal to limit as h approaches to 0. The square of this minus the square of this. Okay, that is 1 plus h square root of 1 plus h means 1 plus h minus 1. Maybe perhaps I'll write it here. Square minus 1 squared divided by h times 1 plus h square root of 1 plus h plus 1. That's what you have. Okay. Again, what I did here was that looks like factors of difference of two squares. Recall from your pre-calculus class that a minus b times a plus b is equal to a squared minus b squared. Okay, that's the formula that I was using. If you have these two factors, that is equal to a squared minus b squared. That is, this looks like a, this looks like a b. That has to be a squared minus b squared. Okay. Now I'll copy this to the other side. All right. Now notice that if I square this one, if I square this expression, you get 1 plus h. You get rid of the square root symbol. H goes to 0. 1 plus h minus 1 divided by h times 1 plus square root of 1 plus h plus 1. Now this 1 and 1 will be cancelled. And then after that, this h and this h will also be cancelled. Right? H is in the top, h is in the bottom. So at the end of the day, what you have is, as h approaches to 0, square root of 1 plus h plus 1, these two will be cancelled. The limit of this one would be 1 divided by square root of 1 plus 0 plus 1. Notice that as h approaches to 0, this will be going to 0. That's why I have 0 here. I have 0 here. Okay. So this will be 1 over 2. Okay. So the derivative of f of x, derivative of my f of x at x is equal to 1 is 1 over 2. So we have the derivative. So now I can find the equation of the tangent line. Of course, I found my f of 1 earlier, that is 1, and f prime of 1 is 1/2. I can plug that in here and here, plug those things here and here to find my tangent line. That will be y is equal to 1 plus 1/2 times x minus 1. Okay, that's the equation of the tangent line. All right, let's move on. Finally, we have this definition, local linearity. We are going to see how to linearize a function near a given point. If f has a well-defined derivative f prime of c at the point x is equal to c, then for values of x near c, this is very important. For values of x near c, the function f of x can be approximated by the tangent line to f of x at x is equal to c with the linearization of f around x is equal to c given by f of x is approximately equal to f of c plus f prime of c times x minus c. Notice that this is the equation of the tangent, right? That we found, that we discussed in the previous slide. This, your original function is equal to that tangent. By the way, approximately, okay? Original function is approximately equal to that tangent for x values near c. What's going on here? If you think of a graph like this, let's say your point C is here. Point C is here. What this tells you is that if I draw a tangent here at the point x is equal to c, for x values which are very close to c, for x values which are very close to c, your tangent and your function look the same. That's what it says. Your function value is the same as your tangent value. For x values smaller, very close to c. Near c, for all x values near c, your function and the tangent line, they overlap. That's what this definition says. Okay, we can use this idea to find approximate function values. Okay, let's look at this example. Suppose that you know that the derivative of f of x is square root. This given function f of x is equal to square root of x is equal to f prime of x. There's a typo here. This should be f prime. Okay. F prime of x is equal to 1 over 2 times the square root of x. Or in other words, the derivative of this function is given to us. That is this one. Use this fact, local linearity, and the fact that the square root of 4 is 2 to approximate the value of 4.1. So a straightforward application of this definition. Okay. So in this case, notice that my value of c is 4. Okay, 4 is the value of c. So I have this linearization. F of x is equal to f of 4 plus f prime of 4 times x minus 4. By the way, I can quickly find my f of 4 and f prime of 4 by plugging x is equal to 4 in this function and in this function respectively. Okay, so if I do that, this is equal to f of 4. If I plug in 4 in this function to find my f of 4, you get 2 because we are assuming that the square root of 4 is 2. This is 2 plus f prime of 4. If you plug in x is equal to 4 in this function, you get 1/4 times x minus 4. This is the local linearization of f of x near x is equal to 4 because your c value is 4 in this case. Okay, your c value is 4. Now we are asked to find 4.1, square root of 4.1. I know that my function, my original function, can be approximated by this local linearization near x is equal to 4. To find the function value at a point which is near to x is equal to 4, what you do is you plug in that value in this linearization. All what you do is you plug in x is equal to 4.1 in this linearization. So you get f of x is equal to 2 plus 1/4 times 4.1 minus 4. By the way, notice that this 4.1 is a point very near to 4. X is equal to 4. Okay, that's why you can do this. If this value is far away from 2, you cannot do this. That's why it's called local linearization. Okay, your x values has to be close to the value c. Okay, now if you simplify this, you will get, yeah, I will let you simplify this using a calculator. Okay, you will get some nice real number, and that is an approximation. Of course, this symbol should be approximation symbol. Okay, please make that correction for me because they are not going to equal it. They are approximations. All right. So that's the last example that I wanted to discuss. With that, we conclude section 2.2. And I'll stop there.